Thank you, everyone. I now request Professor R.B. Bhagat to give overview of the event. Over to you, sir.
Good morning. This inaugural. I'm getting echo.
Sir, we request you to kindly switch on your video.
Okay. Yeah, it's okay now. Yeah. Okay, so I'm
Yes, no, sir, your video is not visible.
okay. It's visible on my phone. Shall I join again?
No, sir.
Can you
No, sir. It's okay, sir.
hear me? Yeah, is it okay now?
No, sir, your video is not visible, maybe because of the internet connection. It's okay, sir.
Can you hear?
Yes, we can hear you, sir.
I'll turn the video off.
Yes, yes, sir.
Okay. Can you hear me now?
No, sir.
I don't know.
Sir, it's okay. You have to talk with your video off.
Shall I go on? Stop now.
Yes, yes, sir.
Okay, so I'm pleased to be present here for the inaugural session to all the dignitaries on the dais, and Professor Kalpana, Bhagat, and Manjunath, and friends. So this is the inaugural day of the joint combined meeting IWMS and ICSE. So the first meeting will be for 3 days, 13, 14, and the second meeting for the following 15, 16, 17, where 15 will be the common the 28th workshop of the IWMS, and it started in 1990 in Tampere, Finland, and it has continued all around the world. And this is the 28th edition of that workshop. And ICNAA started in the first session was held in 2012, and this is the fourth ICNAA. So the origin of the meeting was the community which is interested in linear algebra and matrices, along with later on graph and related areas. And we had participation from almost 11 countries for the IWMS, and also eight countries from around the world for the ICNA. So I'm sure that this will turn out to be a very fruitful event for people interested in linear algebra, matrices, statistics, linear estimation, graph theory, and all the other areas. So I again welcome all of you, and thank you very much. Thank you. Okay.
Thank you, Professor. We now have Professor Sunil Pradhan, who will be welcoming all of you as the chairman of International Organizing Committee, IWMS. Over to you, sir.
Hello, can you hear me?
Yes, sir.
Okay. Um, I'm so surprised about this opportunity that I don't know. I hardly know what to say, but let's say um, 31 years. Oh, now I can see myself there. That is very strange.
You can see you, Professor.
This is like a movie. I'm watching myself performing in a movie. In any case, 31 years ago, the first IWMS was held in Tampere, Finland. Professor Rao was 70 years old then. 21 years ago, the IWMS was held in Hyderabad. C.R. Rao was 80 years old. And so this one here in Manipal is now the second matrix workshop in India. Now, this year, Professor Rao made it 101, for which our society is very proud. I have had the pleasure to attend 3 Manipal linear algebra meetings in person, 2012, 14, and 17, and the online meeting a year ago. Arrangements have been professional. Now again, I have a great pleasure to thank Professor Prasad and his team, Registrar Dr. Sabhajit, for their braveness and courage to take the organizing task. Everything has been proceeding very smoothly for the preparations, and we really have to appreciate local organizers' skills and innards and nerves, taking the terrible times into account that I also express my thanks to the participants. It's the organizers and the participants that make the conference. Thank you, everybody, and welcome.
Thanks a lot, Professor.
evening to all of you. It's my pleasure to welcome you all to the conferences IWMS, ICLAA, and the workshop ACTGMG scheduled in the month of December 2021. Mahe is one of the largest multidisciplinary universities of India with multiple campuses, highest quality of education, and unparalleled student experience. Mahe enjoys a very high ranking by national and international ranking agencies and has the rare distinction of being an institution of eminence, a status accorded by Ministry of Education, Government of India. In keeping with the vision of our founder, late Dr. TMA Pai, of empowering people with quality education and affordable health care, we have been striving uncompromisingly to achieve these objectives of our founder. Center for Advanced Research in Applied Mathematics and Statistics, established in the year 2018 at Mahe with the objectives of fostering advanced research and training in the area of mathematics, statistics, and their applications. It facilitates to bridge the gap between mathematicians, statisticians, and the applied mathematicians working in the area of health, technology, and social sciences. CARAMS regularly organizes national and international workshops and conferences in the focus area which help the promotion of mathematics and statistics at Mahe and also in the region. Mahe would like to thank several eminent mathematicians, government and private agencies who supported the activities of CARAMS by awarding adequate financial grant. CARAMS had planned to organize the conferences IWMS, ICLAA, ACTGMG in 2020 to celebrate and honor a great applied mathematician and living legend, Professor Kalimpudi Radhakrishna Rao, who completed 100 years of his life in the year 2020. Unfortunately, COVID-19 situation didn't allow us to organize any of these conferences and workshops in physical mode. Now we have planned to organize them in the hybrid mode. As on date, more than 200 participants from more than 20 nations across the globe have confirmed attending these academic events. Among Indian participants, almost every state has representation in these conferences. This information clearly spells the quality of conferences and workshops organized by the CARAMS. From the desk of Chairman, Local Organizing Committee, I welcome and also thank all the resource personnel and other delegates participating, and in particular wish a pleasant and safe stay for all the participants attending the event in person at Mahe Manipal during the exciting activities organized by the CARAMS. Thank you.
Thank you, sir. We now have a message from Professor Jia Sharma, who is a director of SMIT Sikkim. He has given his recordings.
Good morning, ladies and gentlemen. A warm welcome to all the participants and the organizer for this particular workshop. It's a matter of extreme pleasure and privilege for me to share that institutes MIT Mahe, Karamas, Mahe, and SMIT under the Manipal Group have joined hands together to organize 2 days event of international repute, that is International Workshop on Matrices and Statistics during December 13 to 15 and International Conference on Linear Algebra and its application from December 15 to 17. I firmly believe that we grow faster when we work together, and I am thankful to Professor K. Manjunath Prasad from Karamas Mahe for taking this initiative to combine the efforts of three institutes under the Manipal Group for organizing this international standard event. Ladies and gentlemen, this particular thing, if we call about matrices, statics, and linear algebra, it is essential for every researcher. This is the basics for mathematical modeling of any model, and this is required in each and every field, whether it is economics, science, physics, chemistry, maths, or any other engineering system. This particular conference is the brainchild of Karamas Mahe and is the fourth in its of international conference that had started way back in 2014. SMIT feels proud and privileged to be associated with the scientific deliberation of renowned mathematicians, statisticians, and research scholars from around the globe. IWMS 2021, that is workshop on matrices and statistics, is the 28th edition of the series of international workshop that started at University of Tampere, Finland in year 1990. And SMNT feels proud for getting the opportunity to be associated with this prestigious event as a co-organizer. I am really delighted and honored and experts around the globe who are going to attend this workshop during next 3 days. Manipal is known for providing the best infrastructure and hospitality to hold workshops and conferences of international standards. But COVID-19 had restricted, and many of you are unable to participate. However, due to this online facility, the number of participation is rather more than what would have been I believe every problem brings plenty of opportunities, and I am sure while exchanging ideas and deliberations during the workshop, participants will look for mathematical modeling and solutions of different challenges and difficulties that world is facing and will come out with probable and perfect solutions. I would like to welcome you all to SMIT anytime in future to hold these events physically once we get over with this present situation. At the end, I wish everyone all the best and a grand success for both the events. Thank you. Jai Hind.
Thank you, sir. I now request all the dignitaries on the dais to release the solemn for IWMS and ICMA. Thank you, everyone. I now request Professor Helmut Brand to give the inaugural address.
Okay, good. No, it's fine. It's fine. I'm here. I have something to hold on. No. So, thank you very much, Doc. Dignities, dear colleagues, dear guests from abroad and here from India, ladies and gentlemen. I'm very honored to give the inaugural address at this workshop and this conference. And I'm from the School of Public Health. What do we do in public health? We analyze data, We try to find out how the situation is, and then we develop policy options where decision makers then take the ones that they think is most appropriate, and then we have to implement them, and then we evaluate. For all this, we need data, so we need your help. And the elephant in the room is the COVID pandemic, and you all, I guess, would have thought about and worked on it, how to deal with the data that are there. I would like to stress today two issues. One is about modeling, and the other one is about artificial intelligence. Let us start with the first. Every policymaker who has to decide what to do in the pandemic for the next months is very eager to get your modeling for the spread of the disease. So you're in high demand. And your methods and you need it to base decisions on. On the one hand, there are different scientific ways to produce models. Yes, we know you do the research for this, and the application. There's one thing that I would like to remember you of. Models are often misunderstood as predictions of the future. And policymakers love to have predictions, what exactly will happen. But that is over-interpreting what you can do. So next to the knowledge how to produce a model, you should have some knowledge of risk communication. How to explain how your models should be used rightly, what they can offer and what they can not offer. So I think this should be part of the curriculum and part of your research too, how to communicate your results of modeling to those who have to base their decisions on your research. The second one is artificial intelligence. In medicine, around 40 years ago, we had what we called eminence-based medicine. An old professor with a long experience in treating patients, when he said, I think this is the disease, that was seen for granted because he has this personal experience. It took several decades to move from evidence-based medicine, where we try to find out via studies, randomized control trials, analysis, meta-analysis, what really helps and what does more harm than good. So it was a long journey from eminence-based medicine to evidence-based medicine. And you are in high demand there too, because we need a lot of people who know about data science, statistics, modeling to do all these things effective that we need. What does this have to do with AI? I'm a little bit worried that AI might go the opposite way. At the moment, artificial intelligence is based on data. You produce algorithms. So it's very clear what your input is. And it's very clear what algorithms can do. But now, when algorithms begin to produce algorithms, we lose oversight. So we can only assume that those things that the algorithm produced by algorithms is doing the right thing. So in a way, we move from evidence-based algorithms, we know what's in there, to eminence-based algorithms, we have no clue what they are doing. And this is a chance and a threat. Of course, the chance is we can produce them much quicker, applications are there, but the risks combined with this is about the application. In some countries, they tried out if algorithms can help us in law cases to predict who will do another crime when they are released from prison. And you see how my mind is. But it didn't work. And if you want to get a life insurance, perhaps there's an algorithm that goes through your medical files. And if there is a little misunderstanding in the algorithms, then perhaps your premium for life insurance will be much higher. So we have to be very careful in this step from evidence-based algorithms to evidence-based algorithms. And perhaps this is something where you can spend some time on, not now, but later, about how to regulate those kind of algorithms that will be used. Can you have a kind of self-regulation? Should this be done by a mathematical society? Should this be done by the government? So I hope this has been some food for thoughts. I wish you 2 days of extensive discussion, even if the things are a little bit difficult with online and offline, but mathematicians are good in their own language, the language of formulas, and this doesn't need no translation. So thank you very much for inviting me, and I wish you good health and a successful conference.
Thanks a lot, Professor, for the encouragement. I now request Professor Sudhakaraji to propose vote of thanks.
Dignitaries on the dais, off the dais, and my dear students. It gives me immense pleasure to propose vote of thanks. Firstly, I would like to thank Dr. Simo Puntanan, Chairman, International Organizing Committee, IWMS, for giving an opportunity for organizing this event. And I thank Professor Susmita Datta from University of Florida for accepting our invitation and attending this conference physically in spite of this situation. Thank you, ma'am. I thank Dr. Helmut Brandt, Director, PSPH Mahe, Manipal, for the inaugural address and his graceful presence. Thank you, sir. I thank Professor R.B. Bapat, Chairman, Scientific Committee, for giving an overview of this event. Thank you, sir. I thank Dr. Narayan Sabait, Chairman, Local Organizing Committee, for his message. Thank you, sir. I thank Dr. G.L. Sharma, Director, SMIT Sikkim, for his message. Thank you, sir. I thank MIT Manipal for providing the venue and Department of Mathematics for extending all the support to organize this conference. Dr. Asha Kamath, Associate Director, who is not here now, I thank Madam for all the support. I thank Mahe Manipal for providing the accommodation and transportation. I thank Avinash Pujari for the arrangement of food. I thank all the participants and I thank one and all. Thank you.
Now let us have a small break. I request all of you to join for back exactly at 10:15.
this building, academic block 3. Okay.
Hello, Dr. Haslet. This is Arni Rao.
Yes. I recognize you.
You can recognize very well. Good to see you.
Can you hear me clearly? Can you hear me clearly?
Yes, I do.
Okay, good.
There is a resound.
Yes, there's some echo. I don't know.
How about you? Can you hear me clearly?
Yes, thanks.
So what's the local time there? What is the local time there?
About 5:30 in the evening.
5:30 in the morning?
Afternoon. Evening.
Afternoon.
Yeah. We're quite civilized.
Yeah, okay.
What about at your end?
It's about quarter to 12 midnight. About 11:30, 11:45 in the night.
I'm not quite clear what the format is, but I thought I would provide an introduction. Then you could talk, and I understand there are questions at the end for 5 minutes.
So how much time I have? Like 30,
Well,
30 minutes?
what I have on my schedule is that you're talking from 10:15 to 11:05, so that's 15 minutes, 50. And then there's 5 minutes for questions.
Okay. So the 5 minutes after 11:05 or 5 minutes
Yes,
before 11:05?
that is my understanding.
I think if everybody mutes, there won't be re-echo.
Yeah, I'll mute when I've finished introducing you.
Yeah, I think the moderator need to mute everybody.
Yeah, no, I think so. I'm just looking down the list at the moment. I think there's only
Is Professor Prasad is there? I don't see.
the center, yeah, Prasad, and then you
Is
and
there?
I are the only others that are not muted. So there's only three.
Professor Army and Professor Haslek, welcome for this particular thing. I'm sorry, Arnie, I'm troubling you. You're attending this one in the midnight. Professor Haslek, I think this is your afternoon. Am I right?
Yes, yes.
Okay. Thanks a lot for joining us. We will have this particular session on time. Maybe Raksha will be welcoming you, and then later we can proceed. Okay. Okay, again, thanks a lot.
Thank you, Professor.
Would somebody let me know when to start?
Yeah, sure.
to the technical session. Now in this session, we have with us Professor Arvind Srinivas Rao from Medical College of Georgia, Augusta University, USA. He is a professor and director at the Laboratory for Theory and Mathematical Modeling, Medical Modeling. He had taught at several premier institutions including the Indian Statistical Institute, University of Oxford, UK, the Indian Institute of Science, Bengaluru, University of Vienna, prior to his arrival at Augusta University. His areas of interest are developing mathematical and probabilistic methods and models, methodologies in machine learning and artificial intelligence algorithms in medicine, biology, etc. To chair this session, we have with us Professor Steve Haslett from Massey University, New Zealand. I request Professor Steve Haslett to take over. Over to you, sir.
Well, thank you for the providing the introduction. I'm pleased to be able to introduce Professor Amit Srinivasa Rao to give his talk on artificial intelligence and possible alternatives, including deep learning machines. Thank you. Professor Rao.
Thank you, thanks to the chair, Professor Haslett, and thanks to Professor Prasad, who is one of the organization, for the kind invitation. I'm really honored to speak in this occasion, on this occasion of 28th International Workshop on Matrices and Statistics. Namaste to all. So my talk, this is based on the last 3 years what I have been doing on fundamentals of what happened to the I hear a lot of echo in my voice. Sorry for interruption. Could you come back again? Namaste to all. I'm really honored to speak in this occasion of 28th International Workshop on Matrices. My talk is based on the past 3 years work that I have been conducting on the machine learning and mathematical foundations of artificial intelligence, and how best we can really train the machines. That's what one of my works I have been working in the last 3 years, apart from other mathematical modeling work. And this talk is based on the overview mathematical foundations of AI.
Sir, can you please switch on the video? Professor Rao?
Hello.
Sir, can you please switch on your video?
It is already on.
Okay, sir. Okay, you can continue.
Just a minute. I'm trying to. video now seen?
No, sir.
Camera is on from my side.
It's okay, sir. You can continue.
It says camera is on.
Sir, please continue.
Thank you. So the current work is based on the 3 years of work on the mathematical foundations of AI, and I will start my slides soon. By the way, there is no I've been disabled to share the screen. They say that only the organizers and presenters can share, but they have not allowed me to share. I don't have option to share.
1 second, sir.
Yeah,
See to that. Sir, please try now.
yeah. Now it is been allowed.
Yes, sir. We can see your screen.
Yeah, you can see the screen. Thank you. Yeah. So the title of my talk is Exact Deep Learning Machines, Artificial Intelligence, and Deep Learning. And I want to thank my recent funders, NSF. The outline of the talk, if we see, first I will speak on the central outcomes of my research in general, and then overview of the where currently the AI stands, the research on AI stands, worldwide status on the AI. And then I will explain the new machines I developed called exact deep learning machines. And also I will discuss the deep learning. So one of the fundamental things I have been promoting at various events is that incorporating actual intelligence. That the original aim of 1930s, 1940s, and 50s and 60s, that those days, those years, those decades when the AI was started, the purpose of AI was to actually behave like a human intelligence. So one of the conclusions that incorporation of actual intelligence to the machine is impossible. Impossible. So nearest alternative to AI, that's what I have been promoting, is called exact deep learning machines. That I will explain at the end of the talk. So according to the predictions, my own predictions and several other predictions, the current state of AI is at very early human baby stage. Very early human baby stage. And most of the research they could at most do is train the machines for a low tech applications. The machines so far could not able to do very high end things, or even high end medium end things also machines could not perform. Whatever the machines performing is at the very low technology things, like cleaning robots, those kind of things. And where does the market and productivity stand? There is also no clarity. Currently, there is no clarity on what would be the AI-related jobs worldwide and how those jobs are distributed by country-wise. There is no clarity on that. But there are only number of publications-wise, there are some research done on the how many countries publishing and whatever research that how many published articles are there by country-wise. That one can know that, but the technology-wise, implementation of the technology-wise, there is no clarity on that. And this is, for example, one of the chip I designed myself, because there is a general feeling that machines behave well better if they are trained in the ancient languages like Sanskrit, for example, because when the wordings of the language and the sounding of the language, there is no fuzziness and there is no ambiguity. The machines will understand better than those languages where the sounding of the letters change with the situation or change with the context. Machines cannot be trained to have a precise behavior. So this is one of the example chip only I designed. That was just to maintain the idea was to understand the complex behavior of the climate. Example chip only. In some in some way, the chip industry, the growth in the chip industry, there is it is about $91 billion market by 2025. There is a prediction of the chip industry market, chip for the AI chips, AI processors. But there is no clarity on who will be using these chips. There is no clarity on what would be the purpose of these processors. Because for high end, this processor, whether these processors will be able to perform better or not, there is no clarity. But for the low end, where only finite number of job job tasks can be given to the machines, they can be performed in a better way. So this is also market prediction only $91 billion chip productions, and these chip productions cannot be automatically associated with the AI market increase in the AI market. And the leading areas where AI systems can be implemented or potential to be implemented, is language and machine processing, virus identification, virus projects, and AI-based toys and automatic machines, automatic vehicles like driving need not be driverless cars, like within a cars with a driver, like lane crossings or automatic brakes or even changing the directions, GPS, this sort of like a low end within a driving system, there is a low end automation can be allowed. AI can be utilized. And the stock market trend. For example, it's still not sure, but several articles are predicting that stock market trend can be predicted using AI. And the low tech industry, as I mentioned before, the low tech industry like cleaning robots and other machines where there is a finite number of things machines can do. Machines have to do where AI has been shown, the AI systems have been showing some advancements. So in general, AI can be adapted, artificial intelligence can be adapted for any situation, for any data. But successful utilization can be seen only where the data and the performance are mathematically associated. Only when the data is digitized properly and mathematically associated, there those situations only we can see that AI is implemented. This is a broader conclusions of the current status of AI. And stock market predictions. I will show a quick example. Suppose we want to understand the future value of a stock using an AI. So that means future value means we want to develop a AI system. So what we do first, we need to shortly solve the influencing parameters. What are the influencing things that influence the future value of a stock? We consulted experts and the other data. We collect everything. Then the data collection is done based on that, and then until certain time point we collect the data, and that data point, then we want to predict the future value. The future value to be predicted, the data point is something, say, 30 stock, and then This area, the data is not being collected because we don't know. Up to this point, we don't have the data. This is a current timeline. The future value, we don't know. This value we need to build. Suppose this is a red line, we want to build the data. The inputs are given up to this point only. So we need to build a.
Sir, excuse me, sir. Other
Sorry.
than speaker, it's better to unmute mute everyone. Voice was not clear, sir.
Thank you.
Please mute other people can mute, please.
Yeah, I think moderators should be the good. So the builder
Sir, while speaking, we are hearing two voices at a time.
Professor, can you hear me? Can you please unmute your mic?
Okay. Now can you all hear me? Can you all hear me?
Yes, sir.
So since the beginning, this was muted.
Ma'am, can you please put your mic off? Because when you are speaking, it is okay. But when sir is speaking, both mics are, we are hearing two.
So in this stock market situation, can we build a mathematical model? The obvious answer is no, because the value of a stock depends on various other factors, which need not have very well defined mathematical structure. So some randomness also involves. And in those situations when there is a randomness involved, using the AI, because AI means when you're using artificial intelligence, that itself, it's with a stochastic model, you would have a lot of uncertainty is added. When you add uncertainty to the AI, the predictions are, we cannot rely on the predictions to buy the stocks or to sell the stocks. So still it is not clear how far AI can be utilized. Although the lot of as the 5 leading areas I showed in the previous slide, one of that area is stock market model. Still we are not sure about the functionality of the AI in the stock market. It's not so far. The chip manufacturing I discussed the processors in the previous slides. So still it is not very clear that this kind of financial markets AI can be utilized, or AI is dependable. Of course, AI can be used anywhere, as I showed in the previous slides. AI can be used anywhere we want, but accurate utilization is what is needed for the successful AI. That's what the chips, that's what the processors, that's what I mentioned all these things. It's not for the utilization of AI, it is for the precise use of AI. So still it is not clear whether stock market models can be predicted with the AI. And similarly for the there's a lot of investment is done since COVID to predict the future viruses and future microbes. So one of the things is that experiments, what they myself and Professor Stephen Kranz, we both published is on the AI in the digital health, and then called digitized medicine, digital medicine. Because one of the things is, the globally there are about 1 trillion microbes are there according to one estimate published in the Proceedings of National Academy of Sciences in 2016 article. So out of those 1 trillion also statistical estimate. This 1 trillion also not a exact accurate number. Suppose we are able to identify all the 1 trillion microbes.
Professor, sorry to interrupt you. Can you please share your screen? It has stopped.
Oh, it's not shared. I'm sorry for that. Now can you see the screen?
Yes, sir.
Yeah. So one of the examples I have been explaining is that AI in virus disease the potentiality of AI in virus research has increased since COVID. So to experiment, one of the things what we published myself and Dr. Stephen Kranz is that suppose you collect all the information about the microbes available in the universe, and they are like that. Suppose this is the hypothetically all the possible microbes. Okay. So once we map its microbes, we take those microbes which are all identified. Suppose we identify all of them. These are experimentally or biologically identified microbes on the earth. There are 1 trillion are there according to the study in Proceedings of National Academy of Sciences 2016. 1 trillion microbes are there. This is statistical estimate, and we all know the accuracy of statistical estimate. This will not be true at all, or this could be true. We don't know. But this is 1 trillion. Suppose we map them. Then, once we are identified them in the labs, we need to digitize them. Unless digitization is not done, we cannot actually use them through machines. Suppose some of them are digitized, the complete information on these are done. Suppose for these microbes which are having the square shaped, we discovered the microbes identified, they are identified through the, these are all identified, the red color squares indicate they are identified, and the yellow colors squares with digit numbers, these are all digitized. Binary codes are digitized, and the white squares indicate they are all being identified. And these are all overall microbes on the earth. So these are the overall microbes on the earth. These are all identified microbes. These are all digitized microbes. Okay? Three types of things are there. So once we identify them and then digitize them, we machines can only understand those which are digitized. Those which are not digitized, machines can never able to use that information for predicting the future microbes. So machines can be trained to understand the combination of the parameters and then train them to understand the future combinations, permutations, and then can be predict. So still, this is the virus. The virus research. A lot of AI has been promoting. The various governments are promoting for utilization of the AI in microbicides. So future, one of the future research also, I myself is asking, recently, I announced a grant and asking about $5 million new grant to understand the AI, to see the impact of AI in virus research, along with some biological collaborators and other collaborators. Suppose we take the RT-PCR and the PCR, and then we collect the data. This is the idea of the project. And then we develop the baseline parameters. And then if several experiments are done, we will have the super parameter space. And though that super parameter space is being trained, use it for training the machine. And machine will predict the future viruses. The broader idea, I'm not going into detail. Broadly, the machine will predict using the super parameter space. Then, parallelly, from these experiments, the combination of the viruses and microbes are developed in the labs, and those information is mapped with the matched with the matching is done with the machine generated viruses with the laboratory generated virus microbes, and you'll see that whether how far the AI can predict. This is the idea, and this kind of experiments are not done before. So that's one of the novelty. This is the cutting edge. This is the cutting edge of the AI, the virus research, so that a lot of investment is done on the vaccines, a lot of investment is done on the treatments, all these things. So hence this kind of experiments are having a lot of future value. And then also all of you know that for the COVID-19, I developed the first mathematical model-based AI that later also adopted as the Arogya Setu in India and various worldwide, that apps and AI, whatever I developed, that became world famous. And then worldwide, I did a lot of consulting for the airline industries, a lot of hospitals based on that. And I'm trying to skip that because we lost a lot of time here. So what I will do is I will give an overview of that model, one slide. So we take a geographical location, and then through the mobile phone based survey, through app, we collect through phone based symptoms, through the phone based interviews, and then through the responses obtained, we decide which of the respondents would need a hospital based testing during the quarantine. And then immediately at the back end in the hospital, the AI would decide which of the individuals would need further testing. And I thought of explaining in detail, but I would like to skip here and then go to the last section, which is the deep learning, exact deep learning machines. So as I mentioned, these exact deep learning machines are best alternative for the AI. That's what I've been promoting. Suppose we have the simple idea is, suppose we have an object with certain finite number of distinct attributes, and these attributes are not dynamic. That means if you want to detect an object, forever the object, the parameters remain the same, not dynamic. In those situations, machine those can be trained probability 1 to detect that object. This is central idea of the exact deep learning machine. That means, again, let me explain the idea. Suppose we have an object, any object, whatever, some some absolute object which can be described with a finite number of attributes. And these attributes are not dynamic. These two are the given conditions. That means attributes don't change over time period. Under that situation, machine can be trained with probability 1 to detect that object. In rest of all the situations, machines can never be trained if these conditions are not satisfied. So this is central idea of the exact deep learning. Suppose we define objective O uniquely defined some attributes y1, y2, ya, and these attributes are, they can be treated like a description of the object. I call it attribute here, but these attributes y1, y2, ya overall describe the object. And let the attribute say yj, we choose exactly one of the pre-decided value c1, c2, cj. So y1 have 1, 2, 3, c1, y2 have 1, 2, 3, c2, and so on. Ya have 1, 2, 3 up to ca. c1, c2, ca need not be same. And suppose machine is trained, and then overall you have a triplet of information o, ay, yc. And the number of all possible permutations that could this particular object O and C1, C2, CA, the product of product of CJ, 1 to E. And then once this information is taken in the previous slide, the omega will set up all the objects in the universe. Suppose omega all the objects of the universe as tag as a O. Because our objective is to detect the object O. So omega will set up all the objects. Then absolute value of omega will be less than or equal to C1, C2, CA, or absolute value of omega will be greater than C1, C2, CA. I'm giving the overall idea of the proof only. And I have one more slide to finish this. And then the idea is to pick an object arbitrarily from the universe and match it with the information already stored in the computer or already stored in the machine. And machine will certainly detect this because these objects are not dynamic. So the given object, the machine will detect whether the object belongs to the omega, or machine will reject that the object does not belong to omega, the set. That with a probability 1. So either the machine will detect or machine would not detect. There is no confusion. There will not be any confusion for the machine. So one of the main advantages of this exact deep learning machines is that there is no uncertainty. Like as I discussed in the classical AI, there is an uncertainty. But in the traditional, this kind of EDLMs or exact deep learning machines, there is no uncertainty. So that's the main advantage. And I'm sorry because of this cross connection and other technical issues, we lost some of the time. So I don't want to delay the other speakers. I want to. So a lot of international sort of media reviewed these works. What are the AI works I published? So you can some of them I covered here. So this is one of the Fast companies, one of the leading technical news magazines, technical news, they also reviewed our work. And then also the campus technology, which world, which US world universities technologies, they also reviewed the AI work, including the Times of India, Jaguar, and then other. About 300 media reviewed this kind of this work on AI. So I want to thank all of them for promoting our work. And I'll be launching a new mathematical journal, which will be a cutting-edge mathematical journal, professional mathematical journal. It's not a magazine, which is called Ganita Prabha. It will be launched soon during the 75th year of independence. So this will have world-class mathematical editors as well as high-class the review board will be there. I'm looking forward to launching the journal, and a formal invitation will come to all of you. And actually, this the background preparation has been going on last 6 to 7 months. So I'll be very excited when I'll be sharing things with you all. Thanks a lot for all your attention. Yeah, any questions, sir?
I think before we had questions, could I request, please, that the microphone at Mahi be turned off?
Thanks a lot, professors, for joining us and for delivering the beautiful lecture today.
Regrettably, I can hear very little. It's endless echo every single time. I'd like, before I thank Professor Rao, I'd like to ask whether anybody has any questions.
Thank you, Professor Hassan. Any questions are welcome.
Well, perhaps since we don't have any immediately, I would like to ask two things. One is when Professor Helmut Brown was talking when we began, he was talking about eminence versus evidence-based decisions. I'd be interested if you have any comment on that. And also, you're developing models for AI, but could you make any comment on the quality of the data input and the effect of that on the results?
Well, these are all very good questions. Evidence-based decisions, that is what I have been promoting. Because if the machines, whatever human do not know, human does not have experience, either through experience or through data collection, machines can never be trained on that. So that's evidence-based, be it biologically. That's what I am promoting, that any information, either through physiology or through chemical technology, whatever we know is very much limited. So using machines for predicting the future viruses, all that, they won't be that easy unless we have a lot of experiments are done on the biologically relevant experiments are done. Now, second part is related to your data quality. Yes, that's also very important. If the data, whatever the information, the parameters are collected based on the data, quality of the data is not properly taken care, the model's always going to affect the parameters are going to affect with the data anyway. And then on top of that, when we are using those kind of parameters, those kind of models for predicting the future value of the stocks or through the climate, the data is not properly clean for predicting the climate. I think AI market is going to affect a lot with the poor quality of data.
Well, thank you. Thank you very much. Has anybody else got a question before we continue? If you do, I cannot see enough of the screen or information here to know who is asking questions. So if you would perhaps turn off your microphone and ask the question directly, that would be good. Well, I don't see any indication of further questions. So what I would like to do, thank you very much, Professor Rao, is thank you for your interesting talk and outlining the possibilities for AI and the complications with it. It's been very interesting. So thank you very much indeed.
Thanks a lot. Namaste.
don't see any questions right now. If there are any questions, you can mail us, then we can communicate with Professor Arno. Thanks a lot, both of you, for joining, professors. We'll start the next session soon. The next session will be from Professor Sushmita Datta. We will start the next session exactly at 11 o'clock.
Good morning, everyone. Hello.
Now with us, we are very happy to have Professor Susmita Datta from University of Florida, Gainesville, USA. She is a fellow of American Statistical Association and elected member of the International Statistical Institute and fellow of American Association for the Advancement of Science. Her constant involvement with big and fat data made her interested in data science. She promotes women in STEM fields. Her area of interest are clustering and classification, bioinformatics, genomics, infectious disease modeling, and many more. We are very happy to have her here. Today she will be delivering talk on statistical analysis of single-cell RNA sequencing data. To moderate this session, I request Professor Arup Bose from Indian Statistical Institute, Kolkata. Over to you, sir.
Thank you. Thank you very much. I've known Susmita for a long, long time, and it's a pleasure to see her again, even though it's only virtual for me. So welcome, Susmita. Please go ahead with your talk.
Thank you. Hello, everybody hear me well? Okay, okay. So let me remove my mask, okay? It's much better that way. Before I start, I would really like to thank Dr. Prasad and Dr. Pontanen to introduce me to this conferences. I have been to this conference last year also, virtually. This one. I wanted to come even last year, but well, nature did not allow me, so this time I challenged the nature. I decided I will come no matter what, and Omicron gave me little hiccups, but then I decided it's not as bad, I'm going. So I'm here. And it's so good to see you all. My talk, unlike the first one, it is going to be little specific, solving a specific research problem, not broad-based. But these are back-end problems. Now you know that COVID vaccine is mRNA-based vaccine. So people like us work at the back end of it, analyzing the data to get things done. And that's what you will be doing. And it gives me immense pleasure to see so many women here. So when we were in the panel, you saw that three of men sitting there, and I'm the only woman. I want this picture to be reversed very soon. Okay, and you can do it all. You really can do it all. Just we have immense potential. Human being can do so much. So think that you can do research. You can take leadership role, being a woman. I have nothing against men. They're fine. They're really fine. And they are the ones giving us the opportunity. So I am obliged to that. But next generation should be different. Okay? It will be at least, if not more, 50-50 distribution should be there. So let me start talking about this single-cell RNA sequencing data analysis. This may be the only talk about this topic. So you know that the central dogma of life, from DNA to RNA to mRNA to protein, that's how, and then protein leads to functionality of the cells. So we are seeing the data at mRNA level, okay, here. Although all the cells of, okay, first let's see, that's where I am from, University of Florida. It is a CTSI, Clinical Translational Research Institute building. Left-hand side belongs to us, fifth floor of that. The right-hand side is aging research. So that's why, and there are creeks full of alligators there, Florida, yeah. It's strange. So that's where we start from. So all the cells of our body have the same DNA structure, right? But why does I cells do what it does, hence do what it does? So only some of the genes get to work in certain parts.
The video seems to be stalled. Video seems to be
identification. So you have started with this collection. Now you can see the groups over here that they are clustered. So subgroups of cells in terms of similarity of the expression profiles of mRNAs. Go to the next slide, please. Okay. So as I said, there is no free lunch. Yeah, it is very good data. The resolution is very good. But as I say, the data is coming from just individual cells, so amount is really minuscule amount, although you have done PCR, but still it may not be enough. So that may give so many missing values, okay, for the gene expressions. And then lots of heterogeneity biologically. Some genes are highly expressed in some cells and some genes are not there. You cannot read any expression from them. So enormous heterogeneity is there. And of course, I have talked about missing values also, lots of zeros. Some of the zeros are biology zeros. Functionally they're zero. Some of them are dropouts, just that due to minuscule amount the machine cannot study. So highly dropout case, and then the data after plotting, you can see that it is not a single modal distribution. That has its own challenges, at least bimodal distribution. So there are missingness, there is modality problems, and there is high heterogeneity or variations. So these are the three things you have to consider. Okay, so this is a simple plot. I gave this talk last year also, some parts of it, so I will go a little faster now. So here you can see that this is the y-axis is the proportion of zeros, and these are box plots of single cell RNA sequencing, and the red ones and these ones are for bulk corresponding bulk RNA sequencing. You can see all the box plots expressions, they are all higher for single cell RNA sequencing. So the proportion of zeros is much higher, this data. And here you can see, without going through this, you can see there are some of them, they are corresponding to bulk cells, and some of them with humps, double humps, they are from single cell. We wanted to figure out whether if removing the zeros take care of this. No, it doesn't. Even if you remove the zero values, still you have for single cell RNA sequencing double mode, at least two modes in the data. And here also it shows the same thing. 1, 2, there's a number of modes, and these are the red ones are bulk RNA sequencing data, and the blue tinges of blue, they are from single cell RNA sequencing data. No, maybe other way around. So you can see the single mode, they are all corresponding to bulk RNA sequencing data. Opposed to that, these red ones, they have at least 2 modes. Okay, so so let's see if it goes. Yeah. So steps to analyze such data. Of course, these are huge data, so you cannot really run the entire samples in one batch. That's impossible. So the data has batch effects. So you have to remove these batch effects, and you have to find out subpopulations of cells, so clustering techniques are done. Identification of differentially expressed genes, this is in blue because we have worked on that. Differentially expressed genes, it's a classic questions that if you have control samples, you have disease samples, you want to figure out which genes are differentially expressed. The same question can be asked at the bulk level. However, single cell should give you better answer because it has the data information from a single cell. Okay, so that's the expectation. We want to figure out if that is true or not. Okay, and then we have identification of enriched pathways. These are post hoc analysis. After you get the result from this, you wanted to figure out that whether the genes that we have found, it makes sense or not, corresponding to the disease. So, and the last one is identification of gene-gene co-association network. What we can do, you know that genes are not all of them are independent of each other. They are functionally related. So you must see some interaction between them. As a data researcher, all we can figure out is the gene-gene association network based on correlation or mutual information criterion, so on and so forth. We will talk about that. Okay? So let's talk about DE analysis. The first talk, you have heard that they were talking about somehow AI will dictate the world, and then you have no idea whether they are doing a good job. As statisticians, we try to analyze the same data with different procedures, multiple procedures, and see what is going on, because there is, in terms of result, of course, there is variability in terms of the way we analyze the data. So there is a competition who can do better, I mean, the same scientific question, but, we keep doing the same, with different ways of analyzing that in order to see where the, many theoretical work, they are giving the same solution or different. If they are giving different, who are doing the best, which algorithm doing the best, so on and so forth. So we are competitors of these three, four. We have thought that they have good statistical background, for analyzing the data. There is always computer scientists, they also do the same kind of things, but they are more algorithm oriented. We are more methods oriented. We try to see whether the methods make sense or not, okay? So that's why. So there are a couple of earlier works which are really good, and we considered them, we wanted to use them as benchmarks. One is SCDE. They are doing this data is actually comes out of a machine as count data. Okay, so naturally they have used the mixture of count data modeling, negative binomial or Poisson. So they have used this negative binomial distribution to account for over dispersion. So you can use Poisson, but the thing is, for count data, over dispersion is something which you need to take care, and negative binomial usually does a better job of handling the over dispersion. And so they have used, wherever there is real data involved, they use the binomial distribution, and then wherever genes they are mostly undetected, they have used low level Poisson distribution to accommodate them. So that's their method. So another competitor, SCDD, they wanted to do a lot of things actually. They wanted to figure out between case and control group, differentially expressed genes, and which is the difference in proportion of cells within the nodes. So it's called DP, and they wanted to figure out difference in number of modes, and then both DE and DBM. This method is wonderful. It's a Bayesian method. This is a directional process mixture of normals, but they have changed the count data to normal distribution after normalizing. So that's the difference. We use still a count data, and this one is good, but they have the computationally, it is so heavy that it hangs up many a times. So it's not really usable. This one is a great way to model this kind of data using generalized linear model. They break it down into two parts. Again, they use but they convert the data into continuous data also, like considering normal distribution. And then they have the first part of the data, that is they fit a logistic regression with so that to the probability of a data that a gene is expressed. That part, they fit a logistic model in that, and conditioning on that, the conditioning that a data, the expression is there, the PDF of the expression, they model it with Gaussian distribution model. So that's their data. We really like this model, and then we modified that quite a bit. What is the modification part of it? The modification is that they assumed that Finak et al. Mast, this is a very highly used method. They assumed that all the genes are independent of each other. But as I said before, it's not the case. Once you figure out the subpopulations of cells within a subpopulation, genes are correlated to each other. So we have the correlated random effects there, and unlike them, we used the count data itself. We did not want to transform the data. So that's the difference. So here you see that the notations YIG, expression counts of gene G in cell I. ZIJ is the indicator that a gene G is expressed in a cell I. So that's the probability. You don't want to throw the data. You have so many zeros in the data which you don't know whether they are really missing or they are just dropouts. So you want to keep them in terms of probability. Once you have the probability that a gene is really expressed, the complement is there also. So you are not throwing the data completely. And this part, CDRI, it is that proportion of expressed genes in cell I. If you include that in the model, we have seen that it works as a normalization, automatic normalization. So it's very important to have that in the data. So what we did for the genes which are expressed, we is a good count data distribution. However, this part is, if we go to the next one, you will see. So this first part is the logistic distribution with, what is that? Theta GI, that what is the probability that gene G in cell I is expressed. That's the part, theta GI, and we have the logit model on that, okay? And the next part, conditional that a gene G is expressed in cell I, we model the mean of gene G in cell I like this. Now, what are these things? This is the regular intercept. This is the slope, that is beta GL. L is corresponding to the logistic part, and then C is for the count data, negative binomial part. Same, this beta GL, beta GC. And these ones are the contribution of the correlated random effects due to the cell I. Okay, so WI is the cellular random effect of cell I, and then this Xi GC is the scaling factor of cellular random effect specifically for gene G. Okay, so we have overall contribution from cell I, and this is through the gene G for that cell. Clear the model? Okay. I really want you to understand this because, you are spending your time here, so you better have some take-home message. Every moment counts. So let's try to understand this little bit. Okay, now this is a specific data. This is, it's not important which data it is. It is scRNA, single cell RNA sequencing data. As you have the PCR in regular data, you have used PCR and you plot the data into two PCR components. These are called TESNI. TESNI or UMAP, they are used for, there are also different dimension reduction methods. They are useful for this kind of data. So PCR does not work. So that's a point worth noting for this kind of data. So this is the control group. This is the treatment group. you can see that these are round ones are cells, different cells. You can see that you can identify different subpopulations of cells, okay? In the control group, treatment group, you can see the subpopulation structure is very different in the two groups, okay? How does it matter? It matters that for us, we are giving correlated random effects. So first, try to do the rough clustering of cells to identify the subpopulations of cells, and we give the, let's say you have K naught subpopulations in the sample group, K1 subpopulations in the treatment group. So the random effect now has two parts, WI, I said the cellular random effect, WI, it has, this is the rough, whatever the random effect the cell gives, the individual cellular adjustment, but this part is the initial estimate of random effect for subpopulation KT. T stands for the treatment group. It can be treatment 1 versus treatment 2 or control versus treatment. So that's the part which does it. Okay, so that's how we are incorporating the correlated random effects. So what kind of distributions we have given? The lambda, the gamma TK, I mean, we are giving IID normal sigma T square. Sigma T square is the, again, T is for the treatment, okay? And WI star IID normal sigma star square. So the correlation between cells within the same subpopulation is given by rho T, okay? If you don't want to really deal with so much, that correlated random effects, you can have alternative methods, that independent random effects, where you just have a random effect with respect to the cells. We don't want to deal with the subpopulations and so on and so forth. So now you have the likelihood of the data, and you want to get the parameter estimates. All the inferences will be done with the beta, two beta parameters that I have said. So you have to estimate that. So we have used Monte Carlo Markov chain sampling for that. That's a natural choice, but it is so slow because the dimension of the data is huge. So you cannot. So what we did, we used we are going through Bayesian techniques, MCMC sampling. So we have done variational Bayes. Variational Bayes is relatively new. It's been there for a while, but not in so much of use. But variational Bayes is a good alternative where you kind of have the approximate distribution. So you obtain samples from that approximate distributions, and it is usually normal. So yeah, end of the day, for the solution, we have to use variational Bayes, because it's whatever methods you propose, it has to be scalable. Otherwise, nobody will use. So that has to be kept in mind. Okay, so in Bayesian, you have this platform where we have this ADV sub-platform for doing the variational Bayes. So these are the steps for applying variational Bayes. And then we are doing the differential expression methods. Consider the cells are, so we are going to find out differential expression methods. So we evaluate the posterior estimates of these betas, as I said, two betas, and then they are the coefficients of treatment indicators. You have the betas from the treatment group and the control group, and then try to do the parameter estimation. So the proposed method for differential expression, you can have two-dimensional what type of statistics. You see that we don't have clashes between, frequentist and Bayesian here. I have just used Bayesian for the parameter estimates. Now for the testing, I'm going to, again, frequentist approach. So in biological data, many a times you have to do that. It's just solving that problem because of that. And so you can have the two different kinds of Bayesian Z-scores. Z-scores is the quiz course you always, figure out. So you have in terms of 2z statistic and find the p-value for this z test. So beta 1g L hat equals 0 and the C beta L, C also is 0. That's the null hypothesis. Now you can do it the two-dimensional test also, where the beta is two-dimensional. It has two components. This is the variance part of it, and this is the chi-square statistics. Okay, there's nothing new in that. Anybody will do that. Now let's see how does it perform. In Bayesian analysis, you have to give lot of, in order to solving the things, you have to give lot of modeling. I mean, you have to give priors on different things. So while giving the priors on over dispersion parameters, random effects, variance, one thing you have to make sure that you use the non-informative priors. You don't want to bias the estimation. So non-informative priors, and you want to have conjugates there, so for the ease of estimation. So we have this long normal distribution, Cauchy. These are the So now we have done the simulation and analysis, the simulation, how we simulated the data. Now, for any, I mean, when you are doing the research, you simulate from your own method, right? And then you simulate for a totally different kind of simulation scheme, generate the data from that kind of thing, and then see how your method analyzes, I mean, estimates the parameters. So and then equal and unequal number of cells, and remove gene expressions in which are not expressed in less than 20% of the cells. We just threw those data. I mean, in genomic analysis, you have to do some pre-screening, otherwise the data is just too big. Anyway, so this is our method, complete random estimation with nearest neighborhood parameter. Why did we just have to nearest neighborhood? These are the tuning parameters, nearest neighborhood 3, nearest neighborhood 7, and this is the true, then independent random effects. Then these are our competitors. I have already talked about. These two comes from specifically created, the ones which are created for analyzing single cell data. HRD, SIG2, some group of data analysts are there who believe that we don't have to really make special methods for single cell RNA sequencing data analysis. We can use just the regular RNA-seq analysis for this kind of data. Okay, so these are the two best methods for bulk sequencing data, and we compare the estimation accuracy, so on and so forth. So this is again the distribution wise, this is the Harvey model simulation, which is our method. I mean, we generate our model, we generated the data from these combinations. That's not important for now. This is the SPLAT simulation. This is very important for anybody interested in doing research in single cell data. SPLAT is a simulation platform which has been thought out very carefully regarding the nature of the data And this is the reference of that paper. They take care of, they have the adjustments due to outlier of genes, dropouts, batch effects, etc., etc. So they have done this. So simulation, I'm not going to, so we generated 100 data sets from each simulation and then obtain the averages of performance measures. So this is the very important results are here. I apologize that they are kind of condensed. It's hard to read. However, I am putting it because our methods give better estimates. Otherwise, I will not have this slide up. Okay. So this TPR means true positive rate. That's FPR, false positive rate, false discovery rate, area under the curve, and number of DE genes. These are the things, and these are the methods. CRE, our method with another clustering algorithm. This is a point to be noted that SC3 also has been made specifically for analyzing single cell RNA sequencing data, clustering method. So we wanted to figure out not only the tuning parameters of a single clustering algorithm, but another clustering algorithm as well. Okay, so you know that all these things make a difference of your results. So we wanted to figure out, and these are just the regular independent random effects. These masked SCD I have already explained. So the performance measures. So true positive, you can see that ours with SC3 clustering algorithm, it works really well. For nearest neighborhood method, they are the same. Okay, it's comforting to see that clustering algorithms are not really changing things up. And then you can see that here they are okay, DE2, they're bulk sequencing data, but they are FDR, false discovery rate is really high over here. So these are very not trustworthy at all. Number of DE genes, area under the curve, ours is a lot better. That's the thing in every case, okay? And these are different Hardy models. This is the SPLAT simulation, which is totally different simulation scheme. Our method is doing well over here too. What is happening? There are these methods, the bulk methods are having very good results in terms of true positive rate, but their false discovery rate is so high that 20% or 29%, so these are not advisable to use. So let's do the, wait. Okay. Now we have analyzed another data set also. Next slide, please. Data set, there is the MSC data from these. I am not going into the details of the data. They are just mouse single cell data. 48 embryonic stem cells for ESR1 and 44 embryonic fibroblast cells. So two kinds of cells. We wanted to see the differentially expressed genes between these two kinds of cell types. That's all. Okay. And again, we have removed some data and we have done the clustering with SNN-click algorithm. Okay. This is, however, I mean, I want to mention that GEO is, these are publicly available data, so you can do it. Okay. So what is happening? That after clustering algorithm was run 3 clusters within the stem cells and 2 clusters within the fibroblast cells. This is the number of differentially expressed genes in between different conditions, but it is very confusing to read this. This is a better plot for the data. What it does, it gives you this plot. This is called upset plot, but it's not upsetting at all. This is really cool. If you use it, this is really good, this plotting data visualization. These are different methods, and you can see that the color code tells you that how many numbers of genes they were detected in one such method. So CRE is our method. You can see that's the winner over here, 1335 genes, and age R is here, single dots, age R one bulk. That's that method. They have 260. What is that? 293. Yeah. Genes, and our competitor SCDE, which is over here, very few. Okay, and MAST is here, very few. But when you take the intersection of all these, then you can see what is happening. So usually it is a better idea to use the genes which are really differentially expressed between different methods. So you have more confidence using those genes, okay? So that's the plot over here. So naturally ours is the winner over here. If any of you are interested, the art package can be obtained from this GitHub page, and this is already, this work is published in Biometrics. These are my collaborators. Okay, now I will go very quickly to a network analysis. Okay, this is the new work. Actually, we have gone even further than this. I will not have time, but this is the network structure, co-expression network structures of genes, gene co-expression networks for single-cell RNA sequencing data. It's called the sparse Bayesian factor model for the hierarchical Bayesian factor model. We call it HBFM to explore the network structure for the associated genes. This is called latent factor modeling. So what it does, it takes care of the, we don't know how many latent factors are there. However, that could be a tuning parameter of the model. It takes care of the gene expressions for each cell to help to accommodate the zero inflated genes and over dispersed. So these latent factors, they control all these things and any other things that you don't even know that there is in the data. So this you can have more latent factors which will take care of this. So gene co-expression networks, the GCNs are constructed by identified pair of genes that have significant associations between them, and you know that for the associations of genes you can have correlation measure as an association and mutual information criterion, partial correlations. There are many methods to identify co-expression, but before that you have to go through the rigorous modeling of the data again. Okay, so and they are available. We have seen the microarray data for bulk RNA sequencing. Also, you can have this, gene association networks, co-expression networks rather. For single-cell RNA sequencing data, by gathering information about individual cells, new opportunities to study the cellular heterogeneity and then a better resolution of GCN. So how it is, note that now I am dealing with a different problem, same research group, trying to figure out, we had to model it differently, just for the sake of the problem. Okay, we said that we don't want to use Poisson, but here we are coming back to Poisson. But it is pretty tricky the way the Poisson model is treated here. So why GI with the count expression gene, for gene G, capital G many genes are there in cell I, we assume each expression comes from Poisson with mean mu GI. The distribution, we are modeling the mean of the Poisson distribution. Beta G is the average expression of gene G. And there is this extra part, F equals 1 to capital F, F many latent factors are there, and then this part is given, just look at this part, lambda IX. So this part is the effect of the factor F for cell I, okay? And this is that, and the power is sitting there, which controls the effect of F with gene G. So this is cell specific, but it is controlled by this alpha GF, the power. So for each cell I, there is the F latent factors, capital F many, and this we assume that these lambdas, they come from log normal distribution. And this mu GI then is this part. What happens, why it is modeled that way? Small values of this one is results into small values of mu GI. Large values of this part, it gives larger values of mean, Poisson mean, which is good, that's what you want. And the variance is this part. The variance is when you have marginal on the Latin factors, they do account for over-dispersion. So this is a Poisson mean and variance, they're the same. So you have this part, but you have this extra part which is like the over-dispersion part. So it is really a clever way of modeling this data. And then if you want to have the correlation measure for the association of gene G and G prime, which is given by here. So the significance of each correlation is determined by analyzing the credible, in Bayesian, frequentist has confidence interval, Bayesian has credible interval. Okay, so credible interval of this correlation measure for this posterior distribution, from the posterior distribution. We have that if it contains the zero, there is no association. If it's not, does not contain zero, then yeah, there is association. So again, the simulation methods from this simulated data sets from Poisson distribution, and all these things are there, and let's see what it is. And then you have these genes are grouped into different clusters. You have that. So, and then different files. I want you to go through. Have I? How many minutes do I have? 10 minutes. Okay. Okay, so we have this three data sets, the same network structure consisting of 350 true ages using this. So we have true 350 ages, that we have 10 factors and varied number of cells that we are just varying them to see whether the number of cells make a difference or not. Number of, just little bit, I mean, I will be done in 10 minutes and you can really have a chat regarding this, okay? Just now, for the time being, listen to this, yeah? Okay. So, the correlation structure that we have over here, we are varying them, and we have the factors, number of Latin factors, we vary them. You want to see how robust is your method with respect to all these tuning parameters, basically, okay? So, let's see. And we have more data sets. We have 6 data sets generated from marginal zero inflated negative binomial distributions via this NOT algorithm. If you want to generate the data from negative zero inflated negative binomial, this is a good place to look for that. This is something you can write it down if you in your research you have that, you can use this NOT algorithm. And then we have this real data, mouse microglia cells, MMC data, mouse brain single cell data set. So we have analyzed all those by varying different Latin factors. And then how we are really saying that ours is good, the performance criterion, the Bayesian information criterion is used to figure out the best model, and then you have performance measures like true positives or things like that. So true positives, we have used a string database that say that which genes are really associated or not, things like that. So the performance comparison, 3 methods of strNA-seq network, association network algorithms. There's LEAPS, the PIDC, SCODE. There are references, I can give it to you if you want to do that. They are our competitors. And then we have also used our bulk data counter parts. We have worked in bulk data network prediction models so much, so we have considered this data. This one is a Bayesian method, so we compared with that. We have used, as I said, string database for really checking which genes are really associated. Okay. So here is the simulation result again. So this lead PIDC, our competitors, and this is our model with F equals factors equals 15. This is the first simulation, 0.76, ours is 76%, opposed to them being so little. And then these are the results for Bayesian methods for bulk data, and they are nowhere near us. So it's really good. False discovery rate is reasonable. It's little higher than bulk. No, not, I mean, even there we are doing fairly well. AUC, area under the curve, we are doing very well. Number of ages, it continues. The trend continues. And then for different factor sizes. But again, established to be the best number of factors with the GIC criterion. Then result for simulation studies of using NORT algorithm, correlated, the negative binomial, zero truncated negative binomial distribution. Again, we are really doing well. These are the pictures, pictorial representations are good to see. This is the true structure, correlation structure of the data. With our method, this is pretty good. I mean, that's what we are finding out. This is again another true structure, but this is another. We are doing quite well over here, but I will show you the competitor, what is happening. For lips, this is the true structure, and see how poorly they are doing here. Okay, so this is the truth, and they are doing like this. So naturally ours are quite, this is an upset plot again for the data set that we are doing. For the data set, upset plot of top 322 gene associations are determined by 7 different methods for MBSC data set that I have talked about. Gene associations are determined by 7 different methods of MMC data set. So 2 data sets are there, and then of course our method is doing the best. I am not going, I can see that you guys are kind of, not having enough attention, so I will really go fast. So the discussion is our method HBFM is able to identify true co-expressions while maintaining a nominal false discovery rate across different number of cells and different network structure, even when the data was simulated from a structure that is different from our simulation, our modeling method. So always you have to do that in your research. You have to simulate the data from your own modeling model, and then you have to do something else. First you check that so that you make sure at least for your method it works well. Okay, and then go to some other methods. So for the true data set, HBFM is able to detect known and predicted protein-protein interactions from string database. Then the competitor network models can be computational, but it is very computationally expensive. So we suggest that you throw some of the genes. For network, it is a usual thing to do. First do DE analysis and make a shorter list of genes on which you are trying to predict the network. So those are needed. If you just run the algorithm with huge data, for sure your computer will hang up, and all these calculations, you cannot do them in your personal computer. You have to use the cluster computer. Okay, so we are still trying to make the method more scalable. So this has been, this is there, the network paper is in PMC Bioinformatics last year. to 2020, and the data set is found with this. The R package of this model that is available through the GitHub, you can check. And if some of you are interested in doing single cell RNA sequencing data analysis, we have published a review paper which has all sorts of methods given at every stage of single cell RNA sequencing data analysis. The so we have that. This is another thing. I mean, I have published a book. I've been working in omics data analysis for a long time. This is in proteomics. I do genomics, proteomics, metabolomics, lipidomics, all sorts of omics data. So this is in proteomics, lipidomics. And I have another interesting career, which is my singing. So if any of you are interested, check this my YouTube channel, Susmita Data Official. So check it out. So you can do it all, I'm telling you. I have raised a kid too, so it is possible. And without any help back there in USA. So, but I still feel pretty young in terms of doing research, and I will keep going. So please keep doing the work. I mean, find life a little more interesting, having another hobby when things are not going well. You fall back to some hobbies, and then just keep going. It's fun to do research. And I want to acknowledge my student who is from University of Louisville. I was in University of Louisville before. He graduated after I moved to University of Louisville. He's an assistant professor there, University of Louisville. Jeremy Gaskins, he's currently an associate professor University of Louisville. Of course, that's my grand, and thank you for your attention. Question.
Any questions, anyone? Yes, Asha Kamath. Please go ahead.
Thank you, Dr. Prasad, for a very overview, a very short time. It's very simple and comprehensive. I just have a couple of I would like to thank research and the data science just highlight the different data.
Asha, your voice is breaking.
Yeah, sound.
Sorry, can you email me the question or something so that I can?
No problem. Sure.
This afternoon you can talk to us.
Oh yeah, this afternoon then I will talk to you. And, because I can't hear the question. Sorry. Thank you. Another question? Hello ma'am, I'm Prabhu, student of biostatistics. Okay. I just wanted to know, the data that's used here is the gene expression data, right? What if you came across what if the gene was silenced? In that case, how is that data captured? Was it used as a missing data, or how was that? Good question. That's in this case, it is hard to figure out whether it is real missing data, like biologically it is missing, or it is just because of how the data was collected, it's just drop out because the data amount is really, mRNA level is so low that the instrument couldn't read it. So it's hard to figure out which is what. That's why we don't really differentiate. We consider them to be what is the probability of non-zero. expression level. But we don't throw those data, so probability calculation takes care of that. So that's how it is handled. So, since the data is not thrown away and also considered, suppose the probability of that zero data was say larger than the probability of non-zero data. How was that like concluded? Like, what was the inference drawn from that? Well, when you are doing the inference at end of the day, I mean, it is on the basis of data values calculated out of the existing data. From the zero values, you really don't have any information from there. And it is this kind of data sets, it does have a lot of those zeros. So that's why the best we can do is to just have them there, but more than that, we cannot do anything about it. Okay? We just are not blindly removing, never do the analysis based on just the complete data. They are there. I mean, the probability calculation, they're there. But it is a good question that how do you figure out which is real missing versus functional missing? It's a tough question, but it is not up to us to figure out. If biologists have some way of determining it, then only we can incorporate. Okay? Mm-hmm. Thank you. You're welcome.
Okay, any other questions?
Question here.
Okay.
Hello, ma'am. Firstly, it was nice presentation. We really enjoyed. And my question is, suppose we know it is over dispersed data. I'm going to use either zero inflated model or any other. Like, can you recommend me any other handy distributions which can accommodate over dispersion other than negative binomial models and zero inflated Poisson and zero inflated negative binomial? Usually those are the popular ones for zero inflated data. I don't know of there may be some other for count data modeling. People always use these things. Yeah. But you have to use it in a clever way. You saw that in the person does not do a good job. Yes. Usually there is over dispersion in the data. But that's why we have used that specific model that for person, or which takes care of the over dispersion. Okay. So it's very individualistic, depending on how your data behaves. You do it and the problem you are solving. But those are the two usual. Okay. There is another one. What is that? CMP model. That is also person. CMP. But that really did not work while we had tried. Okay, so okay. My actual question is, okay, I will assume that there is a over dispersion. I am going to consider zero inflated negative binomial and zero inflated Poisson as two alternators, and that my DIC shows very high for zero inflated negative binomial, but it is comparatively okay to go with the zero inflated Poisson. But the first model identified the negative binomial for that model. How to conclude that, ma'am? It's Poisson has the beauty of mean and variance to be the same. Yes. So if Poisson works well, then I recommend go with Poisson because it's easier to do. Okay. But negative binomial is better. It's harder to deal with. Sometimes you have to just see what problem you are solving and whether you are getting by with Poisson. If you can get by with Poisson, Poisson is good. Okay.
And also interpretation would be different.
That's true. But I mean, of course. In the genomics, you get to handle because of the size of the data. So many things can go wrong, and it's really, I don't have a good answer to that. Thank you. Nice to see you.
Any other questions? Yes, Sushmita, I had welcomed you by saying some words. I never got to see you now. But anyway, very good to see you after a long time again.
Yes, I'm going to Canada. I may see you there too.
Okay. So, any other questions from the audience? All right. If not, then let's thank Sushmita for a wonderful talk and especially the reference at the end of the review paper.
Thank you.
Thank you. Thank you, Sushmita.
Okay, good. So all clear, huh? Not any more questions. Good. I feel good. Thank you, ma'am. Thanks a lot. Thank you, Professor Arabes, for joining us. Without no much delay, let us start the next session. Next session will be contributory talks, and to chair this session we have with us Professor Katarzyna Filipia from Poznan University of Technology, Poland. So in this session we have three speakers. Una Radojic from Vienna University of Technology, Austria. Topic of her presentation will be kurtosis-based projection pursuit for matrix value data. Another speaker is Sandra Ferreira from Center of Mathematics and Application, University of Beira Interior, Portugal. Her topic is prediction intervals in bi-additive models. And the third speaker is Mahendra Kumar Gupta from National Institute of Technology, Jamshedpur. He will be talking about impulse composability in rectangular descriptor system. I now request Professor Katarzyna to take over. Ma'am, please note the third speaker, Mahendra Kumar Gupta, is online now, and okay.
Good morning from Poland. Here we have very early morning, and I will not delay anymore this session. So please, first speaker who is Una Radojic from Vienna. Please start your slide, present your results.
Ma'am, please note, Uma is not online right now, so we will be playing Mahendra Kumar Gupta's video. So we request Mahendra Kumar Gupta to be online now. Please switch on your video.
I'm sorry, but when somebody say want to talk, I can see another speaker and I cannot hear anything. So is there any problem with sound from the server?
Ma'am,
we will sort out the issue soon and we will start the video. Meanwhile, participants, please note we have put the feedback link in chat box. Kindly fill the feedback for all the speakers. Thank you.
Chat box is not about us.
All the participants, please raise your hands whenever you we will address the question at the end of the talk.
Ma'am, if there is any problem in the video, I can give a live presentation also.
Okay, Mahendra Kumar, is it possible for you to give the live talk? Sir? Meanwhile, we will try to solve the technical problem here.
Okay, so
So can you repeat?
so is there any problem in playing the video? I can give a live presentation.
Yes, please. You can play your video and start.
Excuse me, since we have so 15 minutes delay, perhaps we should start. And in the meanwhile, we solve the problem. Mr. Gupta. This is my suggestion. I upload, for example, example picture. I will send it to my center on the UWL authority. So if
Is possible for you to give a laptop? Share the
I'm sorry, I have very strange. I'm not understanding. So, to ask Kunal or Sandra if they can start her job, since we already have this.
Nothing is clearly audible. Every sound is
Yes, you are audible. Share your screen.
okay. I'm doing. So it's visible.
Yes, it is visible. You can start your presentation. Thank you.
Okay. So I'm Dr. Mahesh Gupta from NIT Jamshedpur. Ma'am, my voice is echoing. So is it possible to stop it?
It's fine. Please start your presentation.
Okay. So today I'm going to give my presentation on pulse polarizability in rectangular descriptor systems. So I will explain some terms one by one. So first I will explain descriptor systems. So my presentation is based on control theory, and in this presentation I will show some applications of matrices and control theory. So, so we will see how beautifully we utilize these kinds of applications and time conditions, and we get certain desired results of control theory. So, first descriptor system. Descriptor system are also called differential algebraic equations, and abstract form of system. One A is a part is a dimensional part, and one B is the consistent is the initial condition given for it. Now here are the system descriptions. Use control input. Key A, B are matrices of compatible dimensions. So here we are considering rectangular system of dimension m by n. So it means the number of equations and number of variables are not same. So in many real life applications we see equations where we don't get the same number of equations, and we are dealing with such kind of problems. Now, if M is equal to N, means system is a square, and if matrix E is non-singular, then system 1 is very popular as normal system, and we know it also in the name of state space representations. Now we come to rectangular descriptor systems. So if M is equal to N, means system is a square, and if lambda E minus A, so the determinant of lambda E minus A is not identically zero as a polynomial of lambda, and system 1 is regular descriptor system. So regularity of a descriptor system is necessary and sufficient condition for the existence and uniqueness of the solutions in one case. Now since here we are considering rectangular system, it is possible that there is no solution of the system, and also possible that there are infinite solutions of the system. But here we are dealing with some particular kind of problem which is indices. So that is a well-known problem that impulses arise in the solution of the descriptor system. And here we study how we can study impulses and how we can remove them. So C infinity. So we define some notations here. So C infinity is a set of real valued smooth functions, and then we have a set of piecewise continuous distributions. That means impulses. And then rank of a polynomial matrix is taken as its maximal rank, and then we take initial condition in the form of E of 0, because If we take Laplace transform of 1 or we solve by any method 1a, then we get that the information of ES0 is returned. Information of S0 is returned. So initial condition are appeared in the form of EX0 only. Now, in order to establish some definitions, we consider only homogeneous systems. So let's take first a system without, and if initial condition EX0 is said to be admissible if the system has a solution, whether impulsive or non-impulsive solution, it should have a solution for the system with respect to that initial condition. Now the initial condition is admissible for non-homogeneous system if it has a solution. Now the solution could do both for with respect to that initial condition. Now we come to the another definition, that is no impulsive mode. System is said to have no impulsive modes. System has a smooth solution for every admissible initial condition. Then we come to free of impulse. Now it is a bit stricter than the previous condition. System has a unique solution and it should be smooth for every admissible initial condition. So now we cannot have many solutions. If the system is free of impulse, it should have a unique solution, and that unique solution should be free of impulses. Then we come to the controllability conditions. Impulsive mode controllability. What is impulsive mode controllability? That is, the system has a smooth solution for every admissible EX0. Then we call the system as impulsive mode controllable. And then we come to impulse controllable. If every initial condition exists, it means if whatever the condition is given to the system, whatever the condition, arbitrarily we can give any initial condition to the system and it should be admissible, and then there should exist a smooth impulsive solution of the system. So up to here, definitions are already given in the literature. They exist and we use them for our research. Okay, so now so okay. So following statements are equivalent. So this is the definition. We prove some part of this definition in our another work. Here a system is impulse controllable, and then if it is impulse controllable, that means it is impulsive mode controllable if it admits arbitrarily given feedback. And rank criteria of this condition is given by assertion C. So if system is satisfying the condition C, then we can say that it is impulse controllable. It means there exists a K such that the feedback, the closed pair P comma A plus B K should satisfy the equation C. Now we see that as the condition P or P, they are given in the form of rank of matrices. Okay, so in this form, so we provide this result, and then we design a K here. Okay. So this result we use to our next result, which is the main work of this presentation particularly. Okay, so here, okay, so here we provide the theorem, and we will provide a short and introduction for this theorem. Theorem says that if the condition in the matrix, so let us do some analysis of the previous condition. The previous condition says that if a system is impulse controllable, we can design a feedback matrix. We can design a proportional feedback matrix such that we can make the system free of impulsive mode. Now here we design one more feedback, that is derivative feedback. Now this theorem says that a system is impulse controllable if we can design a derivative feedback such that we can make the system in the form of the previous result, previous theorem. That means impulse controllable. So now question arises: Can we make the system impulse controllable? If it is not impulse controllable, we make the system impulse controllable by giving a proper derivative feedback. Yes. So the condition is given by 4. So if a matrix is satisfying the condition 4, if and only if there exists a K such that the system will satisfy the condition number 5. So we will give a short intuitive proof here, and and in this proof we design a K such that if system is satisfying the condition 4, then it should also satisfy the condition 5. Okay, so the challenge is to design a K. Okay, so by orthogonal transformations, a triple EAB can be written in the form of decomposition 6. Now we will use this standard decomposition here. Oh, okay, so we can see that the result is very obvious because we have a triple EAB and B is assumed to be full column rank without loss of generality, and then the matrix B can be converted to full row rank by applying the appropriate orthogonal transformation, row compression, we call it row compression. And after that we can do the singular value decomposition of the remaining part of the E. So in this form we get the equation number 6, and of the decomposition 6 the proof is given in the reference that is given in the footnote. That is our previous work. So here B1 is non-singular matrix and IR is the identity matrix. So E plus BK, in this form we can write E plus BK in the form of equation number 7, right hand side part of the equation number 7. Okay, so now what we will do, we will put the decomposition 6 in 4, and we will put the decomposition 6 in 5, and then we will see what will happen, what will we get in eventually. Okay, so here we propose that we can take K1 arbitrary and K2 in this form that is given by equation 8. So K2 is taken as B1 inverse E2. Now these things, all of these decomposition, when we put it in condition 4, we obtain that the condition 4 is equivalent to equation number 9. So equation number 9 is rank of A6 equal to rank of A5 A6, and A5 A6 are the part of this decomposition 6. Okay, and similarly, when we put the same decomposition equation 5, we also get the same condition, that is equation 9. So, so here we can say that in this way we design a K such that the equation number 5 is obtained. Okay, so similarly, and then obviously in the paper we prove the other part of this theorem also. And similarly, in the we give one more theorem. Now this theorem says that this theorem is about impulsive mode controllability. So it says that there is exist a feedback such that by designing that feedback, the closed loop pair A comma A plus BK is free of impulsive mode. So now we have one more question. If system is not impulsive mode controllable, can we design a feedback, derivative feedback, such that the closed loop pair should satisfy the condition of impulsive mode controllability? Okay, so the answer is in this theorem, next theorem. Now we provide one rank criteria 12, that is given by 12. So this, if 12 is satisfied, if and only if there exists a matrix K such that equation number 13 is satisfied. Now equation number 13 is the rank condition that we have already provided in the previous theorem, that is condition number B of this theorem. Okay, so we have to make the closed loop triple E plus BK, comma A, comma B, such that this closed loop triple is impulsive mode controllable. So similarly, so the same decomposition we use here, and same feedback matrix K1 and K2 we use here. So K1 is arbitrary, K2 is given, that is given by one equation. And when we substitute these two decompositions in 12 and 13, we obtain 14. And similarly, the same condition. Okay, so and when we reduce, when we put the decomposition, 13 is reduced to 15. Okay, now 13 is reduced to 15, and then we have to put K2 equal to, so then we have to put this equation 8, K2 equal to B1 inverse E2. So when we put here K2 equal to B1 inverse E2, we can see that this top matrix, first block matrix will become 0, and 15 and 14 will be equivalent in that case. Okay, so in future we would like to study these controllability results for discrete time also. Till now we have only studied continuous type of systems. For linear or non-linear descriptor systems, we would like to design observers for time varying linear and non-linear systems, and we would like to develop the similar controllability result for time varying systems also. And then we will see if we can directly apply this theory to some real life applications, or we have some models where these conditions hold. Thank you very much.
Thank you for your interesting talk. Are there any questions or comments? If not, are there any? I cannot see on chat, perhaps in the audience. I cannot see. So thanks a lot to the speaker, and I don't know, in fact, who should I invite now? If it should be Sandra Ferreira or Una Radicevic. So please let me know who is ready.
Una Radajic will be presenting now. We request Una to keep your video on. Mahendra Pahal Gupta, please stop sharing your screen.
Morning. So if you can play my recording, I'm ready to.
Yeah, so if you can start, it would be great.
It's just taking a minute. We will play the recording.
Today I'll tell you something short about the recent work with my former supervisor, Klaus Nordhausen, and colleague Joni Birta. It's about presenting solutions for matrix data. So let's start. In general, a classical problem in image processing is the problem of discriminatory feature extraction. And it is very often that the grayscale images are naturally represented in its matrices, where the value of the matrix at a certain position corresponds to the intensity of the pixel at the same position, image-wise. Some very notable examples are magnetic resonance imaging, MRI, and coronary tissue or CT data. It's very often that, for example, images of some handwritten signs, such as letters and digits, ought to be transformed into a digital format and hence need to be classified before such transformation. Here you can see one such example. These are images of digits 1 and 2 from the online freely available digits dataset, where each image is represented as 16 times 16 matrix of grayscale intensities. This will also be the running example later in the presentation. So mostly traditional statistical approaches involve vectorization of matrix variant observations and then proceeding as in the vector setting. However, it's usually suboptimal for several reasons. So first, let me tell you just something short about the projection pursuit, which is a classical multivariate method for compressing information contained in a three-dimensional random vector into a easy-to-visual, low-dimensional vector. It's mostly also that these projections are also only univariate. However, when we apply projection to pursuit to the data where the dimensionality of the data is large, with not necessarily very large sample size, then we encounter certain problems. So first of all, in regimens where the sample size and as well as the dimensionality of the data tend to go to infinity, most univariate projections of those highly dimensional point clouds are approximately normal, basically meaning that all we find is noise. On the other hand, if we don't have enough data points, meaning that the dimension of the vector p is larger than the available sample size, then we can basically find any two-dimensional configurations of the points using some kind of a bivariate projections. On the other hand, projection pursuit algorithms usually scale quite badly with dimension p. Therefore, in the case where we know that the data admits a natural representation as matrices, so from now on further, I will assume that the matrix X is an observable matrix of dimension p times q. It's natural to work with so-called rank 1 tensor projections of the form U transpose X V, where U is the unit vector in Rp and V is the unit length vector in Rq. So for example, such projections have total of p plus q minus 2 degrees of freedom. Minus 2 is because of the length constraint. And if we contrast that with the standard approach where we first vectorize the matrix X into the vectorized X, then and deal with the standard projections of form W transpose vectorized X, then we are dealing with the projections that are involving p times q minus 1 degrees of freedom. So just to illustrate, if we consider a traditional single horizontal slice of one fMRI image, it's usually 64 times 64 pixels in size. Then this dual projection involves total of 126 parameters, whereas if we first vectorize it and then proceed with the standard approach, we are dealing with almost 4,100 parameters, which is more than one magnitude of difference. So the difference can be quite substantial. So now to conclude this introductory part, the problem that we are dealing with is the problem of unsupervised discriminatory feature extraction, especially in homostochastic matrix variate Gaussian mixture models with two classes. We work in that model for simplicity. So just a short definition, we say that a random matrix follows a matrix variate normal distribution with p times q mean matrix T and the covariance matrix B times meaning chronicle product with A, if when we vectorize it, obtain the standard multivariate normal distribution between vectorized D and B chronicle A as a covariance matrix. This is the corresponding notation. And then accordingly, we can define a Gaussian mixture model, especially we deal with homoscedastic Gaussian mixture models, meaning that both components have equal covariances. And we only observe two-class Gaussian mixture model problem. So what is known, and in the paper that is following this presentation, we also give the proof for it, is that under such problem, I will just describe model level code, matrix variate Gaussian mixture model, shortly MGMM. The optimal projection for separating the parts of mixtures in the sense of LDA is the inner Frobenius product of WLDA matrix and the observable X, where this is the projection direction. Also, it is optimal in the sense that the base optimal classifier depends on the data only through this projection. And then, of course, if the class membership is known, one can construct a plug-in estimate of this projection matrix. However, what we are working on is an estimation of WLDA in an unsupervised manner, especially using projection pursuit approach. So in this work, we consider two novel objective functions or projection indices, both are based on 4 moments of the matrix X. First one is simultaneous index, which corresponds to the kurtosis of the univariate projection, dual projection. And the other one is 1/1 index, where we first estimate left projection direction U using Merida's multivariate kurtosis of the projection as the projection direction, and then we use the same to estimate V, just apply it to X transpose since the method is symmetric in U and V. What we then show is that sequential optimization of both of those indices with a suitable choice of generalized orthogonality constraints, I will talk about this in a few moments, and mixing proportion that is not being equal to these two numbers, these special two numbers, I'll explain that later as well. It then allows the reconstruction of WLDA one rank one block at a time, in the sense that we reconstructed in this manner. And moreover, each of these rank one projections can be thought of as a discriminatory feature itself. So not just when combine all of these into one information. What also we show is that the sequential optimizers of both projection pursuit indices are affine equivariant. So from now on, I was simply focused on simultaneous indexed. However, we show that the results shown for the simultaneous index in an equivalent form are valid for 1/1 index as well. Now, just very shortly about the constraints. So, unlike in standard projection pursuit, we do not enforce orthogonality of the successive optimizers, but with respect to special sets of matrices, those two sets would be G1 and G2, depend on the matrix X. And we say that collection of pairs of vectors U1, V1 to U2, VVD is a sequence of G1, G2 minimizers or maximizers of some function G if the following conditions hold. So first, the first pair needs to be an unconstrained optimizer of the function of interest, and later on, each of the following pairs optimizes the function of interest in U0, and U0 is product of spheres in B, in RP and in RQ, under the following orthogonality constraints, where those matrices with respect to which we observed inner product are defined in the following way, and each of these depends on the previous optimizers, in case it was not clear. So basically what we show is that assuming that the model holds, then if mixing proportion is in 1 minus 1 over square root of 12 to 1/2 plus 1 over square root of 12, excluding 1/2. Minimization of the simultaneous index allows for reconstruction of WLDA in the following way, where we also give the explicit way of calculating the coefficients in the linear combination. If the mixing proportion is such that it's rather small, which means that it's from 0 to 1/2 minus 1 over square root of 12, or it goes from 1/2 plus 1 over square root of 12 to 1, then in that case we maximize, which is also in conjecture with the thought that if the group proportion is, if the groups are kind of balanced in size, then what we do is find a cluster structure. However, if not, then what we ought to is some kind of outlier seeking of the outliers, and it's usually done by maximization of the kurtosis. Okay, so then we compare the obtained results with certain second order methods, and what we show is that the leading projections extracted by the second order methods like MPCA and 2D PCA fail to identify cluster structure even in the simplest case unless some special requirements are met. So for example, we show here that in the case of MGMM, for which the difference in means is of rank 1, MPCA can reconstruct the optimal linear discriminant if the A and B are the eigenvectors of the left and right covariance matrices, respectively. And here we also give the sufficient conditions for this to happen as well. And similar result then holds for 2D PCA projection index as well. So we here see some kind of a benefit of going from the second to fourth order methods. Okay, so now here we observe some asymptotic properties of the estimators. We use moment-based bucking estimators for both the projection indices and orthogonality constraint. And what we show is that the method is the obtained estimators are strongly consistent for the population counterparts, which correspond to the optimal LDA projection directions. If the singular values of non-zero singular values of the WLDA matrix, this is one, are distinct. And the reason we make this assumption is so that we can do the proof. So we use M estimator theory so that we prove that corresponding sample optimizers converge to unique population optimizers. In case that this assumption is not met, then we do not have the uniqueness in the population case. So that's that makes the proof that much harder. And then, of course, as a consequence of this result, we have the convergence of all of the projection directions. We obtain also the convergence of the estimate of the whole WLDA as well. So I will just briefly tell you something about the results that we obtained in the simulation study as well as in the real data example. So one of the two models that we considered in simulations is where X follows matrix variant Gaussian mixture model. The first mean is 0. The second mean in each repetition, and we do, I will show you later, 1,000 repetitions, is chosen randomly such that the singular values of the WLDA matrix are 5 and 3, and the left and right covariances are such that they have AR1 structures with unit variances and autocorrelations 0.6 and 0.3 respectively. So how do we perform a simulation study? So for each combination of mixing proportion and the sample size, we independently generate 1,000 samples. For each of those models, we compute each of the optimizers, U and I, for I is 1 and 2. And then we measure the performance using so-called maximal similarity index between two unit length vectors, which is basically the absolute value of the inner product between those vectors. So 0 corresponds to orthogonality, and 1 corresponds to X and Y being parallel. The following figure, the caption was too large to fit on the next slide. It shows the values of MSI indices for both first and the projection and the second projection directions for all combinations of sample size as well as the mixing proportion. So here you can see the results. Basically, if the groups are and the sample size is very small, then the results are not that good. But even in the case where the groups are very imbalanced, at least the first pair of optimizers is being decently well found. There are some outliers, but in most cases we manage to come very close to the true values. Performance is a lot worse in the case for alpha is 0.2. This is because this value is very close to the value of 1/2 minus 1 over square root of 12, for which we said that kurtosis is value of the kurtosis does not even depend on projection directions because it's fixed to number 3. And then the performance really is very good in cases where we have very groups. In the very balanced groups, we don't even require a very large sample size to estimate the projections well. Here you can see what happens when we combine information from those two estimated projection directions into just one matrix WLDA, where we measure the performance using the square Frobenius norm between the estimated and the true WLDA. And what you can see is no matter how good the performance was in just using just the optimizers, when reconstructing WLDA, performance is somewhat worse. And what we conjecture is it's because the coefficients in the combination of UV transpose when constructing WLDA, these depend on forced moments, which means that then the variability depends on even higher moments, and we speculate that this is the thing that is being hard to estimate. Luckily, what has been shown is that most of the information is actually contained in first few projections, so it is maybe beneficial just not to construct the whole WLDA matrix in practice, but just to observe the first few projections and then draw conclusions based on several projections instead of just one projection matrix. And then the secondly, we demonstrate the performance of the method on the digits data set. We consider a subset of the freely available digits data set, which contains 1,732 pictures. 1,005 correspond to digit 1 and 731 to digit 2. For each, we compute then the estimate of the WLDA, and we projected the data both on the direction of the estimate, full WLDA, and also on the rank 1 direction, corresponding just to the first pair of found optimizer due to what I've said earlier. And then as a reference, we for the data also computed the projection given by LDA and the projection for the first pair of solution found by MPCA, since it's also still what's mostly done is then in unsupervised manner, we use PCA-like procedures to identify structures in data. And then after we've done that, we also clustered the observations along the obtained projections using the EM algorithm. And what we've shown is that the misclassification rate was definitely smallest, and it was virtually 0 for rank 1 projection, a bit larger for the projection on the full estimate, larger for the projection using MPCA, and definitely largest for the LDA-based projection, which gave a surprise. Here you can see how the projections actually look like, where the coloring corresponds to the value of the digit. So this bad performance in the case of LDA basically tells us that data does not really follow the Gaussian mixture model as described, but moreover, it also tells us that this projection pursuit approach is more robust towards deviations from the model than the theoretical LDA is. And just shortly to conclude, so we developed projection pursuit for data that admit natural representation in the matrix form, and for indices we proposed extensions of the classical kurtosis and Matrices multivariate kurtosis, and we showed that both indices are shown to recover the optimally separated projections for two-group Gaussian mixture models in the full absence of any available information, and moreover, we established a strong consistency of the corresponding sample estimators. So here shortly, we conjectured that estimators of WLDA based on this optimization of simultaneous index has limiting normal distribution with standard square root of n convergence rate, and proving that conjecture is a part of the future. On the other hand, what is natural is to extend the proposed method to general tensors to accommodate some more complicated structures like cover images, videos, etc., etc. So in the future, we will aim to tackle that problem as well. So thank you for your attention.
Thank you very much, Una. Very well presented. Very nice topic. Are there any questions or comments? I cannot see anything on the chat. I cannot see among list of participants any right hand. So are there any questions from the audience perhaps?
Participants, are there any questions? I think there are no questions now, so we can go to the next recording of Sandra.
Yeah, okay. So thank you very much once again. Very, very nice. I'm going to ask now Sandra Ferreira to present her results. Correct? Is that correct that it will be now Sandra's turn?
Hello everyone, my name is Sandra Santina from the University of Beira Interior, Portugal. The others author of this work are Professor Dr. Sandra Freire, Professor Dr. Dar Freire, and Professor Dr. João Maxi. Today I'm here to talk about the prediction intervals in B additive models. This is the outline of this presentation on focusing these points. In this work, we consider the additive models which are mixed linear models in which the random part may or may not be normally distributed. The main goal of this work is to obtain the least square estimator for the comments of the random vectors and generalize the least square estimators for the fixed effects vector. Using the cumulance properties, in addition to obtaining prediction intervals for future observation, he also built confidence ellipsoids for these values. We want to estimate the parameters of models of the form like this expression, where x0 and xi are the design metrics. The first metrics correspond to the fixed effects, and the others the random effects are part of model. Beta 0 is the fixed vector. Vectors corresponding to random effects are part of the model by these independent with these independent and identically distributed components with cumulants up to the fourth order. We assume that these vectors have moments until the fourth order. The vector zi have cumulants of the order r, given by this with second, third, and fourth order. The expected value of zi is nu. The Hertz cumulant of the random part of the vectors for the orthogonal complement is given by this, and the linear combination is obtained in this way. We intend to present to use the cumulants in the adjustment of models. For this, the heterospatial choose confidence depend on the cumulants will have a Q rule. Now, let's get into the study of confidence ellipsoids. For that, we take a vector u of normal 1 and we can linearize the problem, and for that, we write the inner product as follows in this way, where the inner product is a linear combination of this and zi, with this product represented by these components. We have that the mean of inner product is 0. This is because the mean of zi is 0, just as the inner product is the linear combination of zi and your mean is 0. Thus, this is equal to a null vector of components C. We have the Hertz cumulant of the inner product like this expression, and we will have this estimator of the Hertz cumulant by R is equal 2, 3, and 4, estimator of skewness coefficient, and estimator of kurtosis coefficient. Consider for an approximation distribution for the inner product, we have this expression, where the estimator of the second order cumulant obtained by this. expression. We have the address expansion of this distribution by this equal, where we use estimators of the CUMEN 2, 3, and 4, as well as the estimators of skewness and kurtosis obtained in the equation 5 of the previous slide. So we get the peak one-time estimate of the address expansion, and with the expression 7 on the previous slide, we obtain this expression by Werner-Brunner. We will now obtain the ellipsoid center on the origin associated with the quadric form by this, which given this vector which minimize this expression. In this picture, we present ellipsoid that pass through to the point in the region given by the vector u at the distance this product from the center. So we got a new way to adjust confidence ellipsoids, and that adjustment we use address expansion. Positional intervals. We present the positional intervals with an approximate probability of containing a future observation. These intervals are constructed for sets of values of the control variables corresponding to columns of this matrix. Given the vector in equation 11, and we can get equation 12, the estimator of the skewness coefficient and the estimator of kurtosis coefficient and the address expansion for this distribution. And using the results in this section, we get this and this in the order to construct the 1 minus p level predictions intervals by this expression, where this is just an approximate value of the probability contained the future observation. Now I present the results. In the order to illustrate the theory, we now consider two simulation studies. Our calculation were using our software. In each simulation, we obtain only one vector for observation, given by the following model with this expression, with this design matrix. We simulate the Z1 and Z2, repeating the procedure 1,000 times. First case, we consider that the random part of the model follows a normal distribution, considering the location and dispersion parameters, with the model described and beta equal 0, and these are random uncorrelated vectors with the no means vectors and a variance convergence matrix I is equal 1 and 2, taking values in this. Thus, by making all the combinations, we obtain the 36 different pairs of independent and identically distributed vectors. In this first case, the second moments of the observation vectors are null. They are null the valence components. Thus, we are to estimate with R equal to and compare the obtained estimates with the previously assumed values. The mean of the estimate obtained for each of the 36 cases, taking into account the various combinations of values previously considered can be seen in the following table. In the order to obtain the confidence ellipsoid that best direction given by the vector rule and the distance by this product from the center, we consider this vector with 6 components, which component begin able to make this value. And taking this equation, thus, one these vectors is like this. We obtain the values of the estimator of the Hertz cumulant, the estimator of skewness coefficient, and estimator of kurtosis coefficient for each U vector. With the value of the expansion of this distribution were obtained the estimate quantities like this and this. In order to this, and consequently this matrix, we consider this for this like this number and obtain this matrix. Thus, the distance of this product as from this number. In order to verify whether the ellipsoids contain dissolved feature observation and 1,000 new observations were generated and count how many times it was weakening the ellipsoids counts. So, how many times we had this inequation? From the following table, we can see that the counting are not far from this number. In second case, we consider that the relevant part of model is distributed according to gamma distribution, where we consider models with the parameters of location, dispersion, and form. For that, we consider beta equal 0 and these taking values in this and b is equal 1. These vectors Zi are random vectors with a gamma distribution, mean new vector, and these variance with these values. And in the previous case, the various combinations for this were considered having 36 vectors of observation. In this second case, everything was simulated and estimated in the same way as in the first case. Therefore, also here, the procedure is repeated 1,000 times, the only distribution and not a distribution normal. The means of the estimates of the variance components for each of the 36 cases are present in the following table. So we can see that means of this estimator are very close to the values previously considered. In order to obtain confidence ellipsoid for future observation, we consider the vectors already considered in the previous subsection. These vectors were considered with the 6 components, which component begin able to get these values. These metrics were obtained as described above, and for this equal like this number, the distance this product as from this number. In order to verify whether the ellipsoids contained in this future observation 1,000 new observations were generated and count how many times it was hitting the ellipsoids counter. So we count how many times he had this inequation. From the following table, it can be seen that the containers are not far from this number. Conclusions. In this presentation, the construction was based on the use of address expansion of distribution, and with these two simulations, it was seen that one may use cumulants for additive models for carry out estimation of the parameters of such model, like the variance components. It is possible to estimate not only the second order moments, but their third and the fourth order central moments, besides the remaining stable vectors. It was to show that the adjustment technique we present works well given an accurate estimate of the parameters for this distribution. We have some reference and thank you for your attention.
Thank you very much. Are there any questions or comments? It was very, very interesting talk. I'm looking on the list of participants. I cannot see any raised hand. I don't know what is the situation in Manipur. At the audience, are there any questions or comments? If not, I would like to thank, I would like to thank all the speakers once again, and see you next time. Thank you very much.
Thank you.
I think we can close.
Thanks for joining us. Thank you so much. We now have a lunch break. So afternoon session will start exactly at 2 p.m.